Hello and welcome back. In 11.3 we work on expected value. So expected value is used to predict the results of an experiment in the long run. In other words, not any single trial, but the usual result over many trials. So sort of leaning on the law of large numbers. So let's do an experiment. So person A and person B have a deck of cards. What they're going to do is draw one card at random. So a well-shuffled deck. If you do 7 shuffles in a deck, it's unlikely that that sequence of 52 cards has ever existed. Kind of a surprising result. But that's a little deeper than this question goes. So we're going to draw one card at random. So if the card's red, A gets $1 from B. If the card is black, A gives $1 to B. So we're going to examine this from A's perspective. A's net gain or loss, which is our expected value, which is denoted with a capital E, not a lowercase e. Probability that A wins times the amount A wins plus probability that A loses times the amount lost. So our expected value, probability that A wins, so that would be drawing a red card. So that would be 1/2. Half of the suits are red, and A will gain $1. Probability that A loses, half of the cards are black, and A would lose $1. Expected value of 0. This is a fair game. A and B have an equal chance to come out ahead or end up with a tie in this game if they play the game many times. So let's change it up though. Let's do a new scenario. This time A gets $1 from B for a club, a spade, or a heart. B gets $1 from A for the remaining suit of diamonds. Again, we'll stick with A's perspective. Their expected value, probability that they win. Now it's 3/4, 39 out of 52 cards. And they win $1. 1/4 of the time they're losing. And they're out $1. They have to give $1 to the other person. They give $1 to person B. So here our expected value is -2/4 or -1/2. If you like it, money, we often go to decimal. So what this expected value actually means, positive, I don't know where I got that negative, positive, positive, positive. So for many plays, on average, you will gain 50/100ths of a dollar per play. Now, there's nothing saying we have to have only 2 ways for the experiment to come to an end. We can do this expected value thing for any finite number of events. Probability 1 times amount 1 plus probability 2 times amount 2 plus probability 3 times amount 3 plus blah 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 plus probability n times amount n. Where p sub I is the probability of the ith event. Similarly, a sub I is the net, that is important, gain or loss. The ith event. So let's do a new experiment. I get $1 from B for a face card. He gets $3 from B for an ace. And we'll give B $2 for all other cards. Again, we'll keep with A's perspective, their expected value, so we can have more than, again, the 2 events. So getting $1 for a face card. So probability of a face card would be 3/13. So Jack, Queen, King in each suit out of the 13 cards in each suit. Net gain of $1. An ace. There are 4 in the deck, which will simplify to 1/13, 1 ace in every suit of 13 cards. Net gain of $3. So then the remainder We have 9 other cards, 2, 3, 4 through 10 in each suit. And we're losing $2 that way. So now our expected value, 3/13 plus 3/13 minus 18/13. So negative 12/13. So this time on average, we will lose 12/13 of a dollar per play over many plays. Now, math tax isn't the only place that we see this expected value. You can see it in test taking. So let's say we have a multiple choice test. And you're going to just randomly guess. So this one, you haven't studied at all. You're going in completely cold. You're just going to randomly guess. And the rules of the road for this multiple choice, a little different than what you might have seen. 3 points for correct answer. 1 point lost for incorrect. And 0 points, no gain or loss. Or a blank. So let's see what our expected value is for a guess. Expected value for a guess on this, and the number of options for each question. So 4 possible, 1 correct on each. So our expected value, a gain of 3 points if we randomly guess the correct answer. There's 1 correct answer out of 4. 1 point loss, a -1 then. Incorrect answer, 3/4. No change for anything left blank. So here our expected value is 3/4 minus 3/4, which is 0. So no gain or loss expected on a guess. So sometimes you can eliminate a wrong answer on a multiple choice. You know for sure that one thing that you see in front of you isn't correct. Well, then our expected value for a random guess, 3 points if we're correct. And now we're down to 1 right answer out of 3. We've identified the 4th one as incorrect. We still lose 1 point if we get it wrong, but now we're down to 2 wrong answers out of 3. And again, the net change of 0 doesn't really tell us anything. So here, 3/3 minus 2/3 is a positive 1/3. A positive expected value, it is to your advantage to guess. So on average, you'll gain 1/3 of a point per guess over many guesses. All right, so let's dip back into the math text. Just lends itself pretty well to this. So let's say to play a game, you're going to buy a ticket for $1. So prize is $100 if they pick your ticket number. And they're selling 200 tickets. Trying to find the expected value of the ticket. So from our perspective, since we're the ones buying the ticket, so we have one ticket that we bought out of 200 tickets sold, and what we'll get out of that will win how much money? Hopefully you didn't say 100. They are going to hand you a $100 bill. How many of those dollars were already yours to start with? One of those was already your dollar. So you actually netted $99 in gain. As far as losing tickets, there's 199 other numbers that you'll hear them and be disappointed. Out of, again, 200 numbers total. That's only going to run you $1, the dollar you paid to play the game. So here our expected value, 99 200ths minus 199 200ths, so negative 100 200ths, negative 0.50. So expected loss of 50/100ths of a dollar. What if we buy 10 tickets? Well, our expected value then, I've got more chances to win. Now I have 10 numbers that I'm hoping to hear out of 200 numbers altogether. Again, if I win, I'm happy. I go up there, they hand me $100, but this time 10 of those dollars were mine. So I've come out ahead by $90 this time. I bought 10 tickets at $1 each. There's 190 numbers that I'm going to be disappointed in. And at $1 each, I'm out $10 if I hear any of those numbers. So our expected value, 900 out of 200 minus 1,900 out of 200. So negative 1,000 over 200, or negative 5. Expected loss of this time $5. And notice that that's 10 times higher, the expected loss for one ticket. So buying more of something that has a negative expected value isn't going to necessarily flip you to a positive expected value. You will just multiply your losses by a factor of however many tickets you purchased. So I'm going to have you all continue on with this same game, only this time so I have you all try similar games. So you're going to buy a ticket for $1, or actually this time we'll make it 50 hundredths of a dollar. Winner gets the crisp $100 bill. And we'll stick with 200 tickets sold. So go ahead and pause it, see if you can find your expected value in this situation. Okay, welcome back. So cap E for expected value. Again, a report just saying just one ticket, 1 out of 200 chance that we win. If we do win, they'll hand me $100. 50 cents of that was already mine. So $99.50 is my net gain. So remember here, net gain, not total gain. 199 ways to lose out of 200 tickets. And if you lose, though, this time you're only out 50 cents. So our expected value here, 99.50 out of 200 minus 99.50 out of 200. Expected value of 0. Expected value of 0 means that this is a fair game. Fair price of these games of chance would be the expected value plus the cost to play. So for example, we'll roll a die. So cost to play, let's say it's $2 to play. And if we roll a 5, they hand us a $5 bill. We roll a 3, get a $3 bill. Anything else, we just walk away. So let's first see the expected value here. So rolling a 5, there's one way to do that out of 6 sides on the die. And they'll hand us $5. $2 of that was already ours. That's really then $3 in gain. There's a 1 in 6 chance of us rolling a 3. They give us $3. 2 of that was already ours. 2 of that came out of our wallet and they handed back to us. Really, we're ahead at $1. So there's 4 other ways to lose. Anything other than a 3 or a 5 come up. And in that case, we're out $2. So our expected value, 3.6 plus 1.6 minus 8.6. So we have negative 4.6 or negative 2/3. So there's our expected value for this game. If I wanted to know what a fair price was, expected value plus the cost to play. So -2/3 plus 6/3, 4/3. So $1.33. That would be the closest to a fair price for this experiment. Okay, so and this is section 11.4, 11.3, my apologies, 11.3. 1 to 4 all, and 5 to 57 on the odds. If you have any questions, please feel free to get in touch. Otherwise, I'll see you next time. Stay safe out there.